Yeah, thanks for introduction. Okay. Hello everyone. At first I would like to thank the organizer for giving me opportunity to talk about my work. So this work has already been presented in this PRB, what I'm going to say today. And it has been done in collaboration with these guys. Jonas is my instructor for PhD and Yuka is my professor, like supervisor, and others are the collaborators. They were in the same group when the project was done. So this is the outline of my talk. At first I will be introducing the terms, like many of you are from theory, so I'm experimentalist, so I will be giving a view of what I mean by single electron box. And then I will be quickly going through large deviation principle. Many of you already know about it and we have already talked for a week almost. So, but just for the sake of completeness, I will be telling this large deviation principle, what is relevant for this talk today. And then I will say something about the observation in the experiment, like after doing the measurement, we get the data, and then from analysis, what are the observations we have. And then the theoretical part will come, in which we try to have a model the system and get some understanding of the observation that we make from the experimental data. And in the end, I will conclude. Sure. So let's start with the single electron box. So in order to explain single electron box, I first need to say a few words about tunnel junction. So we can understand this tunnel junction as a three-layer structure in which there are two metallic layers, and in between this metallic layer is an insulating layer. And depending on what kind of metal we are using, it can be either normal metal insulating normal metal, or normal metal insulating superconductor, or superconductor insulating superconductor, three-layered structure. So for my devices, I use aluminum and copper as these metals. So we know that at low temperature, aluminum is superconducting, so my junctions are superconducting, insulator, and normal metal. And this insulator layer is aluminum oxide layer. So from this junction, we can try to understand the single electron box. It's actually one junction structure. So I represent this junction as this part, like overlap between this lead, something in the left and right, and then this aluminum oxide layer, which is insulator. So in this part, like cartoon structure, this is what I call island. It's not electrically connected to anything. And this I call as lead. It's like quite huge in like dimension. This lead are like connected to some pads which are like micrometer in size. And this island is something like 30 cross 50 nanometers square. And once we understand the single electron box, we can go to this detection scheme, which is just showing the cartoon structure of my sample. So here, this is the single electron box that we are interested in studying, and this is the detector part. It has two junctions, as we see here, and the important part here is that this island of the detector is coupled to the island of device, which is our single electron box. And this coupling allows us to see what's going on in the island of this device with the help of detector. So, this is the only connection we have to get the information of what's going on in the island. So, what we are interested in looking at is that this island can have, it's a normal metal, so it will have a sea of electron, but we are interested in one extra addition or removal of electron from this island, which is visible from the current through this detector part. And when we look at this current through detector part, it gives us something like this. This is not exactly current, but it's some normalized current. So I have some lower level in current and higher level in current. I normalize it to 0 and 1. So, because that's what we are interested in, the two states in the system, and not how it, what is the magnitude. Sorry?
Current going through the island also?
Yeah, so basically your current is from here. So I bias the system from here. Let me go to second slide. Yeah. So, yeah, maybe. So I bias the system from here, this device part, and I measure current in this direction. So, okay, yeah, well, It's much more easier like this. That is my SEP, and this is detector. So I put a voltage bias to this one, whatever bias we want, and then we measure current from here. So no, it's just the electrons are jumping back and forth, and it's like a single electron that is jumping. So you have the current. So you have like 10 to minus 19 order of current. So you can't, like, we can't experimentally measure it. But in this one, you have like something of the order of 10 to the power 7 number of electron that is flowing. So like the current that we get is something of the order of 100 picoampere. So, and why we are doing something like this is that if there is some extra number of electron, let's say n, then it will influence this charge here, and that will like in turn affect the charge there. So that's how our detection method works. Yeah, and well, I normalize it to 0 and 1 just because that's the thing we are interested in, like physics, because what we wanted from this sample and this measurement is that we have a bistable system that stays for over longer period of time. And once we make this device, it stays fairly long time. You can do measurement for hours, and like it doesn't die. So next is my device, like how it looks in like if you look through microscope. So this is like 1 micrometer scale here, and if you look at it, it doesn't look much different, the upper part and lower part, but the way we make the connection, that makes a bit difference. Ideally they both are ICTS, single electron transistors, which is the thing I had there in this part. But here what I'm doing is that I'm grounding the sample, the lead of the sample from both sides. So essentially what I'm doing is that I'm kind of putting both of this part to the same potential. So this both are connected to the same, and then there is only one island. So in the cartoon picture it looks something like this. And here in this part I would like to emphasize this gate voltage. So this gate is something that is kind of coupled to this. So it's like I have this island, and I couple this to a kind of gate, which is essentially a lead, you can say. I mean, we use gate term, and it's connected to this electrical signal which has this voltage generator. So what we can do is that we can vary the potential of this point, and the variation of potential will kind of affect the probability of having 1 or 0 extra electron in the island. That we can understand with this energy diagram kind of. So here what I'm plotting in the y-axis is the energy of this island, and it's a function of this n and ng. N is the number of extra electron in the island, and Ng is a function of this gate voltage, and Cg and E is our electronic charge, this and constant, and Cg is kind of defined by the fabrication process. This coupling capacitance we define when we are making it, it's fixed after we have made the sample. We can of course modify it in different fabrication process, but yes, it's constant over a measurement for one sample. And this Vg is kind of gate voltage that you have free parameter. While you are doing the measurement, you can vary it. So here what's going on is that we have 3 colors, just to show that there are 3 kind of if there is 1 extra electron in the island, 0 extra electron, and -1, you have less electron than the total number of electron. So I will be focusing on this reason. So if you go from 0 to some Ng is equal to 1, then you are kind of making it more energetically favorable to have N is equal to 0 in this region. And when you reach this point where there is a crossover between this blue and green curve, it's the point where both this N is equal to 0 and N is equal to 1 state are equiprobable. What it means that the probability of being in 0 extra electron and 1 extra electron in the island is the same. So you are kind of, when electron is jumping back and forth, the rate of going from 0 to 1 state is same as 1 to 0. At this point where there is crossover between this green and blue curve. And when I go more further away from there, it's like we land up in the region where this n is equal to 1 is more favorable than n is equal to 0. And that also kind of, that's important for me, me to explain here is that because in the measurement we have tried to, with different gate voltages, to have different transition rate between the states. So this is the experimental part. And now I will go quickly to this large deviation part. So, I mean, this is quite well known, and it's already, it's nicely presented in this report by Hugo. So here, what I'm taking is, So here in this part, what I'm taking is that Sx is my independently distributed random variable, and then I'm kind of summing over all the Sx for n number of, so I'm taking n number of this Sk and making a summation over them. And when I take this average and put it to plot, it looks something like this yellow curve. So yellow is basically what we get when we take n number of random variable and then just plot this distribution of averaging. And this blue curve is what, blue curve is what this central limit theorem will say that it's a Gaussian. And here, my x-axis is S over n and y-axis is this probability of S over n. In linear scale it looks fine, but when I go to logarithmic scale we start seeing some deviation of this distribution that we get from taking just random variable, and the Gaussian will look something like this because it's logarithmic scale, so it's just this parabolic thing that should be visible in logarithmic scale. So this tail part is explained by this large deviation principle, where instead of having this square term, we have this generating function, and then it kind of takes into account this deviation part as well. So why I'm putting this here is that for bistable system, this generating function is an ellipse, and that was one of the aim to see this ellipse behavior in physical bistable system, like in experiment, can you get this or not? So this was this PRL by Jordan Sukharov in 2004, and he said that in the paper it was like if you take a system with two current values, like some averaged over I1 and I2, then you kind of get in large time limit, you get this kind of ellipse behavior of the distribution. So if I kind of compare this to, then this yellow curve is the one that is plotted in this one as this solid line, black line. And okay, now I am moving towards the, sorry? Well, there is this, this one, you mean, this one. So you would expect something like, something like this tilt to be somewhere in the center, or? Well, that asymmetry is defined by the ratio of this transition rate that I will be going in detail further. And you can have this symmetric one as well if you tune your gamma such that they both are equal. So at this point, I will make a connection between the variables that I used before to explain this, or this large division principle, and the variables that I will be using later on. So this n there will change into tau. There was n number of parameters, the n number of Sx variable that we were taking. Here I will be taking the time window over which I am averaging my points. And this Sk will be transformed into It, I is this one, and this I is varying from 0 to 1 with some noise in the system because of measurement, experimental noise. And then this S over n, that was the average of total number of variables that we have taken, will be transformed into this time average of the current that I have from the system. So essentially this is like logarithm of p of this I tau over tau in the y scale, normalized to this term, tau multiplied by gamma's product. And then on this right hand side is the ellipse equation, like T naught is the initial time. You can, like when you have these traces, you can take from 0 to 2, 1 to 3, 4 to 4 to 6. Yes, so you have like different points because you need to have more averages so that you can have a proper distribution, like number of data points. And okay, and this theory should be ideally valid for all the bistable system, and bistable systems are very common. You can also see, like if you look at these references, you can see it in the biological system. They also have this defolding and folding of molecules. So one such system is this one that they have studied. It's also from this Jordan-Sukharov group. And then here they have demonstrated in this paper that you can see this ellipse behavior in this kind of current when you obtain from the system. So their system was kind of semiconductor-based quantum dots. And okay, they have this similar kind of time traces that we have in our system. And then this ellipse were something like this. So here I think I can answer your question that they have this different tilt of ellipse. Like it's not the same, this kind of tilt. So this tilt variation is because of this gamma. If your probability of being in higher state is more, then it will be more tilted about the higher one as compared to the lower one. So, I mean, it's doable. People can observe this in the experiment. So that's one thing that we wanted to do. And here is the list of things that we wanted to investigate in this project. First was to see this universal ellipse, as they call it in the paper, like if it is visible. And then the second one is this crossover between the short time and long time statistics. So in the short time, if we just look at this picture, we see that it's like, if you take the distribution of it, it will be two Gaussian distribution. Like this one and this high level and low level are the ones that are there. But if you go to higher one, like higher integration time, they see that it's an ellipse. So it was one of our aim to like see how does this change occurs from this peak to kind of ellipse. And then once we have attained that, to kind of understand theoretically, like how can you get it from do you have an equation which has this kind of limiting case? And then the next one was to see once we have this probability distribution, do we get any symmetry property of the distribution? Something like fluctuation theorem they have in entropy, this as a function of entropy. So, well, this just to remind what is the variables. This is the average current, and when we do it over very long time, so this by long time I mean something like 1.5 second in my measurement, where my transition rate is of the order of 100 Hertz. So when we do that, we kind of get quite nice ellipse. Here, this circular one with this open circle are the one that we get from measurement, and this solid line is just to demonstrate that it's an ellipse. And the equation is taken from this Jordan-Sukharov paper, this one, this here. So this we got already, this universal ellipse, we saw it in our system as well. Now we were interested more in seeing how do we get from the short time to long time statistics. So when we average it over like 2 milliseconds, so we just take the whole time trace, put it into a small section of 2 milliseconds and take the average within that point, that range, then we kind of get these distributions. So here, I mean, from theory, if you look at the thing, it should be a delta peak, because that's how we say that it's either 0 or 1, but in experiment you have some noise, so it's like distributed a bit. And this is just to show like in logarithmic scale of y, how does it look. So when I proceed from this 2 millisecond to 80 millisecond, I kind of see that my distribution is becoming smaller. That's because I'm kind of averaging over the noise. So it's like my current are something like 0 and 1 plus some noise there. So when I'm doing this averaging over 80 millisecond, this kind of is this thing is spread is reducing, and then I'm getting kind of peak behavior. And also we see that this number of these numbers are increasing here. But in linear scale, you see that nothing is here. It's like almost zero level, like it was here. But in the logarithmic scale, if you see, it was kind of flat here, but now it starts to have something in the midway. So if I go higher in integration time, something like 320 milliseconds, then I start to see some kind of development in the midway, and these peaks are becoming kind of lower. So the peak the numbers which were contributing to the peaks are somewhere going in the midway, and in the logarithmic scale, it's quite visible. So when I go from this 320 millisecond to kind of 1 second, then I see very nice distribution. In the logarithmic scale, it looks almost like Gaussian, and then in the linear scale, you kind of see these kind of rare events as well. So once we have this, like we have observed this one, we wanted to have a theory to explain this, what's going on. So we had, this slide is just to show like how the development occurred from 2 milliseconds to 80 to 320 to 120. 1280. So now we go to the theory part. So for explaining the theory, we consider this model in which we have a classical two-level system, and since it's a two-level system, we kind of have this summation of probability of being in either in one or in the second state as 1 all the time. So it's given by this one, and then the rate equation is governed by this one. So I can maybe try to explain it a bit. So let's say I have two states, and the rate of going from here to here is something like gamma plus, and this one is gamma minus. So if I want to see the probability, evolution of probability of being in this state, it's something like, or is it one? Okay. It's something like summation of this, all the channels through which it can come to state this one. So gamma minus probability of being in 1, like this is the rate through which it's coming to this state 0, and this is the kind of probability of being in this state before, so that it can come to this one, minus gamma plus probability of being in 0. So it's like this kind of say you, what is the rate of going away from this state and times the probability that the system was in that state before coming from there. So that's what this rate equation essentially means. And after using this model and multi-jump approach, we obtain this kind of distribution. And yeah, the derivation is there in the supplement of the paper. And here, if you take this regime in which this gamma plus and gamma minus, like these two rates are equal, then you can recover the equation which they presented in this article back in 2009. So their system was kind of different from our system, but then they kind of observed similar behavior for this state in which both the transition rate are almost the same. So now I will try to explain this equation a bit. So if I look at it, I can kind of simplify, not simplify it, but put it in terms of these three terms. So first is just prefactor, and there are two competing terms, T1 and T2. So A is just the prefactor that was there, and it's a function of this gamma, that is the transition rate, and the tau. So this term in the plot that we have from experiment just contribute to the 0 level of the distribution. So when we have this kind of distribution, it's this part that this A is contributing to. And this term, first term is kind of delta in I and 1 minus I, and then this gamma minus and gamma plus. So this first term is independent of tau, like how much time you are averaging, and only thing it depends on is the transition rate. But the second term is kind of higher order in, linear and higher order in tau. So in the prefactor of T2, you can already see this product of gammas and tau. So they kind of grow very fast with tau. And this I0 and I1 are the modified Bessel function, and this x, the argument of this Bessel function is kind of a combination of this gammas and tau, and also the variable I. And this Boxer function is a product of these theta functions. It's to restrict, if you look at it, it's just restricting my current to be between 0 and 1 as it should be, because that's the variable that I have. But from here, if we can't get the distribution that we get from experiment, because in the experiment I have a noise to begin with. I don't have either 0 or 1 state. I have some noise in the system. So we needed to incorporate somehow this noise thing as well. So to do that, we put the histogram of this one without taking any averaging time, and then we see that like the noise for both the state are Gaussian, and from this like fitting Gaussian you can extract the sigma, and then what we do is that we take a convolution of the distribution we got from previous distribution and the distribution of noise. We take a convolution between them, convolution of that, and then we obtain some p tilde I tilde, which is kind of the distribution including the noise in system. And then for this theory for this theory equation, all we need so all we need is this gammas. Our I is this x-axis parameter, and then tau, what is the averaging time we are using. And if after incorporating this noise, we need the sigma that to be there as well. So these are the 3 parameters that we need, and we can extract all 3 of them from the measurement data. So kind of there is no free parameter in this theory that we need for fitting. And this gammas I calculated based on the time system stays in a state. So let's tau to be the time it stays in the state, higher excited state or state 1, or and then we make a list of all the tau 2 before it goes to the transition, and then take average of it and then take inverse of it. Then it gives us this rate of going from 1 to 0 state. That's similarly we do it for this gamma 1. Gamma plus, which is like going from 0 to 1. We take this tau 1, we make a list of tau 1 and then average it and then take inverse of it. So all the 3 parameters can be extracted from the experimental data itself. And now when we put it to the equation, this in short time limit, as I explained, this T2 term is very small because this product is less than 1, and then I have multiple order of this term here. So this T1 term is kind of dominant one. So what we get as a distribution is mostly this term that is contributing to the distribution. And here the circles are from the experimental data, and the theory one is the solid line. So they matches quite well, I would say. So this is for this small time interval. When I go to higher time interval, it kind of fits quite nice as well. So you can, it's the same. The circles are from experiment and the theory is solid line. And in this regime, we recover the same equation that we should have from this PRL 2004 by Jordan Sukharov. And now just to give it how it looks for other ones, it matches quite well for this other time, integration time as well. So at this point, we kind of understand by theory how to obtain what we get from the measurement, like all the different time distributions. So yeah, at this point, I would like to say something about this ellipses, like what are the parameter defining the tilt and the width of ellipse. So I just simplified this equation. I just rearranged the terms in this equation to put it in terms of ellipse equation, and now we have nice y minus y0 divided by b square plus x minus x0 divided by a square is equal to 1 equation for ellipse. And if we look at this one, we kind of see that this width of ellipse is defined by this product of gammas, and the position of this ellipse, this y minus y0, this y0 x0 coordinate is defined by this kind of function of gamma, combination of gamma, And then this tilt, the place where it kind of makes the tilt, is defined by the gamma ratio. And that we can understand from if we think about it, it kind of makes sense, because if you are taking a lot of distribution of this 0, 1 variables and you start summing up all of them, it should pick up at one value which is like more closer to the more probable state. So after this, what we did is that we varied these gammas and see if it makes if we are what we are understanding about this place where it picks up, does it make sense? If we vary gamma, does it behave as we expect it to be? And it seems to vary quite. It seems to act quite nicely, because this cyan one is kind of one in which only this probability of being in 0 state is much more higher than being in 1 state. So this 0.15 is kind of showing you the probability of being in state 0 divided by probability of being in 1. So when we go from this lower number of this ratio to higher one, we kind of see the dominance, like this height of peak varying. And now what we wanted to do is that we have this equation. So can we somehow, we have this gammas that is defining this ellipse. So what if we try to make a transformation such that these gammas are taken care of, you kind of subtract this effect of gamma? How does it look? So we defined this kind of transformation. We just subtracted this y0 part out of it. So this one from the y-axis. So now what we see is that all of them lie on the same semicircle, on one semicircle. And here it kind of makes sense that on this part only this red one is dominant, and on this one only blue one is, cyan one is dominant, because you don't have that, this doesn't go that far in I, and this red one doesn't go that far in I either, because they are the one, they are more probable. So we kind of say that we find a universal semicircle, and so we understood this point, and now we wanted to see some kind of, if there is some symmetry property of the distribution. So we obtained this kind of relation, which is not exactly which looks like the fluctuation theorem, and it's somehow similar to this Galois-Cohen relation that they have. The only difference is that in this Galois-Cohen you have this entropy as the parameter here, but I have something that is we can understand as deviation from the average current. So this I bar is kind of average current, which is 0.5, and this J is kind of how much you are fluctuating away from it, or in both direction. And sure. So this is something that we obtained. So this kind of is an inspiration for my next project as well, in which I'm trying to see this fluctuation relation as a function of entropy. So I kind of try to get a system which I can measure entropy from it. So, well, this is my conclusion. We kind of obtain this universal ellipse behavior, and then understand how it goes from short time to long time, and then we obtain a fluctuation kind of relation in long time limit. So, thanks.
Questions? Comments?
Experimentally control the transition by just changing the voltage.
Yeah, get voltage. Yes. Yeah.
So, can you think of a generalization to going beyond the two-state system? Can you have cases where you have 3 states?
Like in this one, I have the variables that are 0 and 1.
0 and 1, exactly. So can you think of exponential generalization of interest where you have more than 2 states? You have 3 states that you can.
Yeah, it might be, you can maybe do it, but it's a bit more complicated, because here you have only 2 systems, 2 states, so it's easier to map back and forth. But when you start to have this kind of 3 states, let's say 0, 1, and 2, then you kind of have 6 transition rate to take care of. So that's a good question. You can do it, but you haven't done it.
Is it possible to fabricate? Is it of interest?
Yeah. I mean, in my system that I'm working on now, it's something like this kind of one.
I see.
So what I have is that I have two islands. Let's say M and N is the number of electrons in each of the island, and I have detector 1 coupled to this one. That kind of says what is going on in this island. And one detector is coupled to this one, which kind of says what is going on in this one.
Right.
So in this one, actually, well, it's quite nice. You have this kind of 4 state of the system.
4 states, okay.
So 1, 2, 3.
Okay.
And it's very nice, but it's much more complicated because I have 12 rates in that system.
Yeah.
So,
Okay.
but it's fun. Yeah,
You
we
can
have.
do this. We'll talk.
Yeah, we have it. Yeah, it's nice. We have it. Yes. Yeah, by this transition rate, you are trying to tune this P0 and P1, how it is distributed. I didn't get the second part. Well, you can vary this. Okay, so maybe I didn't explain. Yeah. Yeah, so when you are controlling this transition rate, you kind of controlling how long it stays in one state as compared to the other one. Yes, yeah, you can always do that. You just vary the gate position. So I can maybe go back to that slide. Yeah, so what you have to do, like this gate position is like, if you take from 0 to 1, sorry, it should be 1 here. So when you are in this place, this n is equal to 1 is very, I mean, it's usually not there. So when you go to this gate position, you will only be on one state. You will stay there. Power of what? Sorry.
The time in which it stays in one of the states.
Yes.
Right now it's exponential.
Yes, yeah.
But he's asking, can you make it power down?
Well, I don't know. Well, I have to think about it. Sorry. Maybe later I can answer your question. Yeah.
Okay, so if there are no more questions, let's thank Shilpi.